I hope you guys are having a great weekend. Today we're going to be entering into the next part of rational expressions. We're going to be looking at rational functions. So we're going to be looking at the graphs and the different characteristics of rational functions. So a rational function is a function in this format. So if we have function f is in the form of one function. This would be function n over another function, function d, where function n and function d are polynomials. Here's a graph of function f, x plus 3 over x plus 2. Here's the graph. Okay, so a couple things that I want to bring to your attention about this graph is, okay, we have the graph is decreasing here, and it's also decreasing here. Okay, the center point is a very important point for translating our graph. The point that's directly between the two curves. That's a very important point. Let's talk about the domain. How to find the domain of this graph? Well, if I put my pencil down, remember there's arrows on the ends, which means it infinitely goes on to the left and to the right, and infinitely down and up. Okay? But the point is that as you go along here, the x's are getting bigger, and then x approaches some number, and then it kind of just like hops over and continues on. So what is it hopping over? Well, again, that's why I bring up this little point here. Okay, if you know the x coordinate for this point, you know what the domain is not. If you know the x coordinate of this point, you know what the domain is not. So we know that this point here is -2, 1. So graphically, we know that the domain does not include -2. Does not. The domain of a rational function includes all real numbers except x values that make the denominator 0. Okay, well, what does that mean? Well, let's say you don't have a graph and you need to write the domain. So you take the denominator, okay, and you set it equal to 0, and then solve for x. X equals -2. Okay, so the domain is going to be all real numbers except x cannot equal -2. And so a very easy way to write the domain is to put x cannot be equal to 2. This is the assumption that all other numbers work. All other numbers are in the domain. The only one that is not in the domain is x equals 2. What would make the denominator of function f equal to 0? We've answered that question, -2. We also find that answer right here in our very special point in the middle of our two curves. Okay, if function f equals function n divided by function d, if they have no common factors, then the graph of function f has vertical asymptotes at the zeros of d of x. Okay, so let's talk about this. The zeros of d of x. The zeros of d of x are going to give us the vertical asymptotes. Okay, vertical means up and down. So we're going to have a vertical asymptote at the zeros of d of x. Okay, now notice it says function n and function D have no common factors. Well, let's take a look at our function. X plus 3 is the factor on the top, and x plus 2 is the factor on the bottom. Do they have common factors? No. 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 So, to find the vertical asymptote, we want to find the 0 of d of x, which is in the numerator. I'm sorry, excuse me. D of x, apologize for that. D of x is in the denominator. So the 0, to find the 0, we take the denominator, we set it equal to 0, and we solve. Okay? This is where the vertical asymptote goes. So we go back to our graph, and we put in our vertical asymptote. Now remember, vertical asymptotes cannot be crossed. They're lines that the graph gets very, 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 very close to, but never touches. Gets very, very, very close to, but never touches. Vertical asymptotes can never be touched by the graph. So I'm going to write that down here. Can never be touched or crossed by a graph. So our vertical asymptote is x equals -2. Now do you see the relationship between the domain exemption and the vertical asymptote? Do you see the relationship? This is the equation of the vertical asymptote. Here's the domain exception, and notice it goes through the points -2, 1. So all of these are related, domain and the vertical asymptote. Okay, let's see if I can make this a little clearer here. Guess not. Let's try that. There we go. It says identify the vertical asymptotes of the following graphs. So what we're looking for here is we're looking for where is this graph getting closer and closer and closer and closer to. So it looks like it passes 0, so it looks like it's getting closer and closer to 1. So this graph is getting closer and closer to 1. And check up here as well, it looks like this one's getting closer and closer to 1 as well. So our vertical asymptote is going to be directly in between the two parts of the graph. Here's your vertical asymptote. Okay, let's go ahead and write the equation. That would be x equals 1. X equals 1. Okay, you would do number 2. Let's take a look at number 3. This one has 2 vertical asymptotes, 2 of them. Okay, on the left side, if we go directly between the two parts of the graph, okay, I don't mean to make my vertical lines touch the graphs, but if they do, it's only because of my pencil is so thick. So this one actually has 2 vertical asymptotes. One at x equals -2, and one at x equals 1, 2, 3. Okay? So that would mean we'd have 2 domain exceptions. Okay? So our 2 domain exceptions would be x cannot equal -2. Okay? And x cannot equal 3. Now remember, where do we find these exceptions? We find them in the denominator. So what would the two factors be that would give us an exception or a vertical asymptote of -2 and 3? Well, it would be x plus 2 and x minus 3. Because if we set this equal to 0, we would get x equals -2. If we set this one equal to 0, we'd get x equals 3. Now remember, this is an exception because it doesn't touch. The domain does not touch -2. The domain does not touch 3. So the domain does not include -2 and 3. This means all real numbers except -2 and 3. Look at there. It says match the graphs with the rational functions. We've already done this. This is going to match with graph number. We just talked about that. Now, why don't you match the other two? So we know this one's going to be number 3. Which of these is 1? Which of these is 2? All right, moving on. It says state the domain and find the vertical asymptotes for the following rational functions. So first off, we're dealing with the denominator when we're looking for the domain and when we're looking for the vertical asymptotes. We're dealing with the denominator. Okay, here we go. Remember, real simple. We take that denominator, make sure there's no common factors here. Okay, they're different. X minus 2 and x plus 2, they're different. And eventually when they are the same, I'll explain what happens then. So x plus 2, first step, set it equal to 0. Okay. So when you solve that, you have just given me the vertical asymptote. Now, the domain cannot include this number because there's an asymptote there. So x cannot be -2. X cannot be -2. So all real numbers except -2. Remember, we cannot divide by 0. If I plug -2 in, we get 0. Division by 0 is undefined. Again, division by 0 is undefined. That's why there's a vertical asymptote. It's impossible to divide by 0. Let's take a look at number 5. Here is one where we need to factor first so that we can see the factors. Remember, we have to make sure there's no common factors. So let's go ahead and factor the top, x plus 3, x minus 3. No, we're not going to get away from factoring. You will all be factoring giants by the time you leave this class. X plus 2, x minus 2. Now, do we have any common factors? No. But we do have two factors in the denominator, and so we set each of them equal to 0. Okay, so how many vertical asymptotes are we going to have here? 2. X equals -2 and x equals 2. X equals -2, we'll have one vertical asymptote. X equals 2, we'll have the other. So that means that the graph cannot cross a vertical asymptote. These domains are exceptions. Looks like I'm running out of time. See what you can do with the rest of these, and let's talk about it tomorrow, first thing. Okay? Hope you're having a great weekend.